So I thought I'd sort out a bit of confusion with regards to this question, because I was freaking confused for a long time. Um, so if you have a 5 kilogram spherical ball rolling down a 45-degree incline, what maths can we do with that? So what physics can we do? So first off, we draw a diagram showing all the forces present. So we have gravity, we have the force due to the normal force due to the incline, like the surface, and then we have the sum of the forces is the mass times the acceleration of the ball, which is just the final acceleration. And then we have sine mg, which is just the parallel component of the force due to gravity. The force, so that's parallel to the incline. And then we have friction. Well, how do we know that there's friction? Because we know that there's no slipping. And if you think about it, if there was no friction, if we slathered this ball in oil, then the ball wouldn't roll. It'll just slide down the incline. So we know that there's friction. And so yeah. Now what else can we do? Well, we know that the torque is equal to I, the moment of inertia, times the angular acceleration. And we also know that the torque is provided solely by the frictional force, right? Because that's the only force acting on the ball. So the frictional force times the radius, because it's acting at the radius, at the surface of the ball. So we can equate those two. I times Fr equals that, right? And then we can actually eliminate this. Now I'm gonna go through like how we eliminate that. How can we relate this over here to the linear definition of acceleration? Now, so down here, xt equals r times the angle. Now, if we look at this diagram over here, if we have a ball, say that we're rolling, it rolls from t equals 0 over here to t equals whatever over here, and it rolls out this distance xt. What is that distance xt? Well, we know that if you remember from year 11, that the arc length is just r times theta, right? So xt equals r times theta t, where theta is a function of t. Now, the velocity is just the derivative of that, while r is a constant. That's the only thing changing, so that's just the same as r times the derivative of that, which is angular speed, right? Then same for acceleration, we just differentiate that again, and we get r times angular acceleration. Sometimes that'll be r times alpha, right? Because alpha is an alternate notation for angular acceleration, whatever floats your boat. Okay, so now that we've done that, we can get rid of this over here. We can get rid of that, and we can say, well, Fr equals I times Ax, there, the acceleration down the slope, on R, right? Because, yeah, right? So now what's I? Well, I for this specific case is 2/5 mr squared, because we know it's a solid spherical ball. If it was a cylinder, it would be different. If it was a ring, it would be different. If it was a yo-yo, it'll be different as well. It depends on what object is rolling down the slope. So then you just simplify that again. Fr equals, you just sub that in, equals that, simplify down to F equals 2/5 max, where ax is the acceleration down the slope. Then you sub that back into this original equation up here, and you just solve for ax in terms of, so you end up getting ax equals 5/7 sine theta g. We know theta is 45, as stated in the original question. Hence, we can solve for the acceleration down the slope, the linear acceleration. Similarly, if we want to actually find out the friction force, well, rather than resorting back to like our definition of friction, which is F equals the normal times coefficient of friction, that'll be useful later. But like we already have a function for friction over here, right? And we already know what the final acceleration is, so we can just sub that in, and along with this mass over here of 5 kilograms. And then from that we can work out the rest of the stuff. But yeah, just this sort of, these two formulas over here, really handy, especially knowing like why this is. I don't know, I think that's very important. But yeah, good luck guys, happy studying.